Okay, so I just want to give you a brief introduction to this course that I'm going to start teaching on Monday. So the course website will be available to you very soon. This is available on GitHub. I will send you the link as soon as I release this video. And on this web page, I will provide all the materials, the course materials, and the exercises that you will do in class, and other materials such as case studies and so on. It also has the approximate schedule for the week and the material that we will cover in the whole week, and some additional readings that I suggest for after you have finished the course. Okay, so what I want to talk about in this video today is some background information that I will assume on the first day and after the first day. So this background information is probably known to you, but I just want to quickly review it so that we are all on the same page as regards the terminology that I will use in the lectures. So there are two foundational ideas that I will cover on the first day. The first idea here is the idea of a random variable. I'm not going to walk you through the details here. If you already know what a random variable is, then you should go back and review your understanding of it. If you don't know what a random variable is, I'm going to start from the very beginning and unpack this idea for you. I just want to alert you to the fact that I'm going to discuss random variables on the first day. Okay, so that's one thing. The second thing I'm going to discuss is maximum likelihood estimation theory. So this is a very important concept that you need to understand in order to understand how Bayesian statistics works. So I will talk about some fundamental ideas there, but one aspect of maximum likelihood estimation theory that I think everybody is probably aware of is how to calculate a sample mean. The formula for a sample mean is shown here in equation 5. So if you have a vector of x data points, let's say these are continuous values, and the length of the vector is n, you sum up the data points and divide by n to get the sample mean, which is supposed to be a maximum likelihood estimate. And so I'm going to explain tomorrow, so that is on Monday, what exactly that means and where this idea comes from. Okay, but I'm sure that most of you are probably familiar with this idea of mean. The other maximum likelihood estimate that you must have encountered in the past is the variance estimate. So this is the equation here in equation 7. If you have a sample mean that you've computed from a vector of scores with length n, then you take the sum of the square differences between each of the vector values and the sample mean, and you divide by n-1, and that gives you the variance, right? Take the square root of the variance, you get the standard deviation. Now there's an issue about whether you divide by n or n-1. So these are the equations 6 and 7 in order to compute the variance estimate. I'm going to talk about all that in class, but in essence you do know the formula for computing estimated variance given a data set. Okay, so these are two basic concepts: random variables and maximum likelihood estimates. We will review this on Monday. Okay, so I'm not going to talk about those things too much yet, but I do want to talk about the central limit theorem, which states that if you have a vector of scores that you've sampled from a population, just like this x that I'm talking about here, this is supposed to be a vector of n data points. Okay, so if you have a vector of these scores, and if you take the sample mean of that vector, you've got one sample mean from that one experiment. But you could, in principle, repeat that experiment multiple times. So let's say you repeatedly run an experiment and you get multiple samples repeatedly, and each time you get a sample, you compute the sample mean. An important assumption I'm making here is that each of the data points in the sample is identically distributed. It's coming from the same distribution, and each of them is independent of the other data points. So in statistics, we say that we are making the IID assumption, independent and identically distributed assumption here. Okay, so I've got repeated samples of sample size n from the population, and I'm computing the sample mean each time. So what I have in the end is a vector of sample means. Okay, if I plot the distribution of this vector of sample means under repeated sampling, the central limit theorem states that if the sample size was large enough, the distribution of these samples under repeated sampling will be approximately normal regardless of what the underlying distribution of the data was. So the data could be exponentially distributed, it could be log normally distributed, it could be gamma distributed. It doesn't matter what the underlying distribution is. If the sample size is large enough, the distribution of the means under repeated sampling is going to be approximately normal. One caveat here is that the underlying distribution that you're sampling from has to have a mean and a variance defined for it. So there are distributions like the Cauchy distribution which do not have a mean and variance defined for it, and so in that case the central limit theorem does not apply. Okay, anyway, so this is called the central limit theorem, and so what it implies is that if we have under repeated sampling, if you have a vector of means and the central limit theorem tells us that this vector of means is approximately normally distributed, we can compute the standard deviation of the sampling distribution of the means under repeated sampling. So this standard deviation of the sampling distribution of the means is called standard error, and there is a closed form formula that takes as input the standard deviation that we just computed in equation 7, right? So the square root of sigma hat squared will give us the standard deviation estimate. So that's what this is what we see here, divided by the square root of n. This formula gives us the standard deviation of the sampling distribution of the means, and this standard deviation is called the standard error, right? So there's actually two standard deviations involved. One is the standard deviation which we estimate from sigma hat, which represents the standard deviation or estimates the standard deviation of the underlying distribution from which we are sampling the data. But there's another standard deviation of interest that's called the standard error, and this is the standard deviation of the sampling distribution of the means under repeated sampling. Okay, so there's two standard deviations involved in the whole story. All right, so given this standard error, so what we do when we do an experiment is we have a sample means, we estimate the sample standard deviation, we know the sample size. There are three pieces of information that we extract from an experiment, and given the standard deviation estimate sigma hat and the sample size, we compute this estimated standard error, right? And what this gives us is the ability to write down an uncertainty interval around the sample means. So if the sample means is mu hat, we can, if we write plus minus 2 times standard error, what we have is a 95% confidence interval that covers 95% of the area under the curve in a normal distribution. Okay, so this point I will revisit in class, of course, but I do want to remind you, if you've already seen this before, I want to remind you that we have a 95% confidence interval around the sample means, and this gives us a measure of the uncertainty around the sample means. Okay, all right, so one interesting question is, what does the confidence interval mean? I will come back to that when we start talking about Bayesian credible intervals. I will remind you of this equation 8, in that discussion. Okay, now what I wanted to cover today, to just make sure that we are all on the same page, is the underlying logic of a frequentist hypothesis test. So the null hypothesis significance testing NHST framework works as follows, and as an example I'm going to take the one sample t-test as a representative case of the null hypothesis significance test. Okay, so suppose that we have a random sample of size n, and the data are coming from a normal distribution with mean mu and standard deviation sigma. So these are two unknown parameters that we are going to try to estimate from the data that we are getting. Okay. Of course, I'm always assuming that the data are independent and identically distributed. Okay. I won't say that again and again. Please understand that as being true even if I don't say it. So once we have such data of sample size n, we can estimate the sample means, which is x bar, the formula I showed you earlier, and we can estimate the standard deviation, which I'm writing here as sigma hat. So this allows us to estimate the sampling distribution of the means under hypothetical repeated sampling. So remember, when I described the central limit theorem, I was talking about actual repeated samples being taken from the population and calculating a vector of means each time. Okay. In reality, we don't do repeated experiments. We do a single experiment. And the cool thing about the central limit theorem, what's beautiful about it and what gives us incredible power for doing hypothesis testing, is that from a single sample, once we've estimated the sample mean and the sample standard deviation, we know the sample size because we decided on the experiment, we can describe, or we can get an estimate of the sampling distribution of the mean under hypothetical repeated sampling. So we haven't done that repeated sampling. From the single sample, we can kind of figure out, or we can figure out what the estimates are of the sampling distribution of the mean. In other words, we can figure out what the estimate of the true underlying mean is, which is x. Our estimate is x bar, and we can figure out an estimate of the standard error given sigma hat and n. Okay, so using this equation. So what I'm writing here is an estimate of the distribution of the sampling distribution of the mean under repeated sampling, under hypothetical repeated sampling. So the null hypothesis significance testing approach works as follows. We set up a null hypothesis that states that the true unknown mu that x bar is an estimate of has some fixed value. So for example, a typical assumption made is that the null hypothesis is that a mu is equal to 0. So what this null hypothesis is actually stating is that we are assuming now that the true distribution of the sample means is approximately normally distributed and is centered around 0. That's what that null hypothesis means. And it has the standard error that we will estimate from the data. Okay. So the intuitive idea for null hypothesis significance testing is that if the sample mean x bar happens to be near the hypothesized mean mu, which is 0 in our null hypothesis here, we have the hypothesized mean, we've got the sample mean, which could be very near this hypothesized mean, or it could be very far away from this hypothesized mean, right? So if the sample means is near the hypothesized mean, we are going to assume that the data are consistent with the null hypothesis distribution. If, on the other hand, the sample means is far away from the hypothesized mean, then we are going to assume that the data are inconsistent with the null hypothesis distribution. That's the null hypothesis significance test. So the problem now is, how do we formalize the idea of near and far? So it's easy to say, oh, this is near, this is also near, this is also near, this is also near, but this is far, right? So how do you decide on a cutoff, right? So the way to formalize this is to say the following. We are going to now talk about the distance between x bar, that means our sample means, and the true mu. So we're going to try to figure out this distance, x bar minus mu, in standard error units. So we're going to say that the sample means is t standard errors away from the true mu that we have hypothesized. Okay, so this null hypothesis mu. So this t value is going to quantify our distance in standard error units from the hypothesized mu. Okay. So this brings us to the t-test. Okay. So what we're really going to compute is a quantity called the t-statistic, and this statistic is basically a transposition of this formula 12. Basically, I'm dividing both sides by the standard error, and what this gives me on the left hand side is the t value. the t statistic, and on the right hand side I get this term here, which is x bar minus mu over the divided by the standard error. So we are going to call this t value, which is derived from the data. We are going to call this t value the observed t value. We observe it from the data. This observed t value under repeated sampling from the population will have some distribution, and that distribution can be described in terms of a random variable. Sorry, this is a typo here. It's not variable but variable. This can be described in terms of the random variable t, right? And so this random variable describes the distribution of the t-score under repeated sampling. So instead of small x bar, I'm using capital X bar because I'm talking about the sample mean as a random variable if I'm repeatedly sampling from a particular population. This is a fixed number mu, which I have hypothesized to be 0 in this particular example, and the standard error is the estimated standard error in this example, estimated from the data. Right? So the point is that the observed t value that we get from a single experiment, you have to think of it as an instance of a continuous value that we have observed from a random variable capital T, which describes the distribution of the t statistic under repeated sampling. Okay, so this t distribution is defined in terms of the sample size. So it takes as parameter the sample size n, and what we write formally is that the t distribution is being generated from a distribution that takes as parameter n minus 1, right? So n is the sample size, so we subtract 1 from it, and that is the parameter that goes into this t distribution, which is written small t here. So I'm sorry that it's a bit confusing that I'm talking about the observed t value here with t, and I'm talking about a distribution here with t as well. What I should have technically done is written t subscript observed here, right? In equation 13 I should have written t observed. I will fix that in the LaTeX file just now in a few moments, so you'll have the correct file later on. This small t is referring to, this small t here is referring to the distribution that takes as parameter n minus 1. N is the sample size. Now what I mean by parameter is the same thing that I mean in a normal distribution. The normal distribution takes the sample mean, it takes the true mean, and it takes the true standard deviation, so mu and sigma, as parameters. Once you give those two numbers to this function, which is the normal distribution, you will get a certain curve, right? So in the same way, the t distribution takes a parameter n minus 1. Okay, so we are at this point that we have computed an observed t score. Well, what the heck, let me just fix this right now. This is kind of annoying to see this incorrect thing right here. So I'm just editing the equation now in LaTeX so that we can see the correct thing. It's just irritating me that I'm not seeing the correct term here. All right, here we go. Let's go back. Where are we at? Equation 13. Here, right? So from a particular sample, I'm going to compute the observed t value, and this will be the basis for us doing a null hypothesis significance test. The basic point will be that if the observed t value is large, that means the distance in standard error units between the sample mean and the hypothesized mean is large. And so if the observed t value is large enough, we are going to reject the null hypothesis that we set up, this null hypothesis here, because our sample means is far away from the hypothesized mean, right? So the question still remains, what is far away enough, right? So that's something we still have to formalize, but the point is that we're going to use this observed t-score to make that decision whether to reject the null or not. Okay, all right, so here we go. One detail I want to mention is that this this t distribution that I just mentioned here, this t distribution will approximate the standard normal, that is the normal distribution with mean 0 and standard deviation 1 as sample size approaches infinity. Of course, you're never going to have infinite data, but this is a limiting case that I'm describing. As sample size goes to infinity, the t distribution becomes identical to the standard normal distribution. Okay, just a side note, not important for us right now. Okay, so the null hypothesis testing procedure now means it goes as follows. We define a null hypothesis. For example, mu is equal to 0. Given data of size n, sample mean x bar, standard deviation sigma hat, or I'm writing s here now, it doesn't matter what variable you use. You compute the estimated standard error s over square root of n. You compute the observed t value. Again, I've made the same mistake here. It's pretty annoying. Right, you compute the observed t value and you reject the null hypothesis if this observed t value is large. Okay, so now we have to decide what large means. Okay, and for this we need to define a rejection region on the t distribution that we are looking at. Okay, so what we are going to say, just approximately, is that for large sample sizes, if the absolute value of t is 2, we will reject the null hypothesis. Okay, so where is all this coming from? Where this is coming from is that we are going to decide that there will be a rejection region in our t distribution which will have this approximately normal shape, right? We are going to decide to reject the null hypothesis if the t value is larger than 2. So the absolute t value is larger than 2. That means if the value is smaller than -2 or bigger than +2, right? That's what I mean by absolute value of 2 being greater than absolute value of the observed t being greater than 2, right? We will reject the null hypothesis in that case. So why did I decide on 2? That is something I will discuss in more detail in class when we discuss distributions, the normal distribution in particular. Okay, but right now you can trust me when I say that a t-score, an observed t-score of greater than 2 allows us to make a decision criterion that we will reject the null. Okay, that's the basic idea here. So the basic story is going to be given independent and identically distributed data, y, a vector of scores y. So earlier I was using x, now I'm using y. I'm kind of keep changing the variables. You shouldn't get confused by the name of the variable, right? I will make it clear what I'm talking about each time. So I have some data y, and this is independent and identically distributed. So I can use this R function called t.test on this vector, and what this t.test function will give me is this observed t value, and if this observed t value is larger than 2, I mean the absolute value is larger than 2, I will reject the null, period. That's the null hypothesis significance test for us. Okay, all right. There are some variants on the t-test that you should be aware of. So if you have paired data, if you have repeated measures data from 2 different conditions that subjects have seen, then you have to give the 2 vectors side by side and write paired equal to true. Alternatively, what you can do is, since these are paired vectors, each row in the vectors is coming from the same participant, what you do is you do a row-wise subtraction and take the difference between the vectors and give that to the t.test function. Right? There's also a third way to write a to use the t.test function. If you have in your data frame a vector of y-scores and you have another column which tells you whether it is from condition A or condition B, what you can do is, oh, there's a redundant comma here, I'm sorry about that, but what you can do is you can simply say y as a function of, so that's what that tilde does, of the column called condition. Okay, so I will show you examples of all this in class, but there are different the different kinds of syntax that you can use. For the simple case where you have one vector, you can just use this one sample t-test. If you have repeated measures, there's 3 different ways in which you can do a paired t-test. Okay, but the basic logic is always the same. We're gonna get an observed t-value, right, and we are going to decide to reject the null if that t-value, the absolute t-value, is greater than 2. That's the whole story there. So what's the last thing I want to discuss now is the following. When you do an experiment, you compute your observed t-value and you make your decision. I'm going to reject the null or I'm not going to reject the null. Okay, so that's what I've shown you in these 2 rows here. When you do an experiment, there's only 2 choices you have as an experimenter doing null hypothesis significance testing. One is to reject the null if the absolute t-value is big enough, and the other is to fail to reject the null, right, if the absolute value is smaller than 2, right? So these are my decision outcomes. These are the possible decisions I can make, but in the real world out there that I'm trying to guess the properties of, so you see that I set up a null hypothesis that mu is equal to 0 in my particular example. Okay, but it's not necessary that that's the truth about the world. So there are 2 possible situations in the world. The null hypothesis is either true or the null hypothesis is false. Okay, so in the columns here you're seeing 2 possible situations, 2 possible states of the world. One of the states of the world is that the null hypothesis is in fact true, and the other possible state of the world is that the null hypothesis is in fact false, even though you are assuming that it's true. Okay, in our null hypothesis significance test, we are going to assume that the null is true and then do our test, but it's not necessary that the null is true. Okay, so we could be in this world and we could be assuming that the null is true. In that case, we have screwed up. Okay, we could be in the other world where the null is in fact true, in which case we haven't screwed up, we made the right call. Okay, so but we don't know which world we are in. Okay, all we have got is the observed t-value, and we're going to make our decision based on that. Okay, so we can talk about now what will happen if we repeatedly run our experiment. Just remember that in real life you're never going to repeatedly run an experiment, or almost never, right? You run your one experiment and that's all you have, right? But the logic of hypothesis testing in the NHST framework is assuming that you can repeatedly run the same experiment, and we talk about the properties of this repeated sampling. Okay, so the properties of the repeated sampling are as follows. If the null hypothesis is actually true, and in your one particular experiment, if you decide to reject the null, you would have made a mistake, right? So under repeated sampling, the probability of your making this mistake will be some probability value alpha. So probability has to lie between 0 and 1. So this number will lie between 0 and 1, right? And this probability of incorrectly rejecting the null when the null is actually true is called type 1 error, or alpha. Okay. An alternative situation is that you run your experiment, you reject the null, and the null is actually false. Okay, so in this case you correctly rejected the null. The probability of your correctly rejecting the null is going to be called this quantity here, and it's called power. Power is going to refer to your probability of correctly rejecting the null, where the mu has some particular true value other than your hypothesized null hypothesis value. Okay. So think about the other scenario now. So we've covered the two possible scenarios where the null could be true, the null could be false, and what you actually decide to do under repeated sampling is to reject the null. Okay. If you reject the null under repeated sampling, with some probability you will make a type 1 error, and with some probability you will have power of which will be a certain probability, right? So the probability of your being able to detect an effect that is actually such that the null is false. Okay. Now think of the situation now where the null is actually false. Okay. You've set up a hypothesis test where the null is true. You assume that the null is true rather, right? But the null is actually false in reality. You don't know that, of course. You run your experiment and you fail to reject the null. So your observed t-score, the absolute value is less than 2. So you fail to reject the null. So if you fail to reject the null, you might think that, yeah, that's the same thing as accepting the null. Okay, so let's take that as true. Okay, so let's say that you want to accept the null now, right? You would be making a mistake. Why? Because you're in this column. The null hypothesis is false. So you've made a mistake. Under repeated sampling, there will be some probability of making this mistake, and this is called type 2 error. And this is written down as beta conventionally. Okay, so there are three quantities that we are very interested in: alpha, type 1 error; beta, type 2 error; and 1 minus beta, which is called power or statistical power. Okay, so these are the things we're interested in, and graphically what this amounts to is the following. This figure is very important to internalize. Okay, so what this figure is showing what this figure is showing is the hypothesized null distribution. You can see here, this is the hypothesized null distribution, right? It's centered on 0. This is the t-distribution. Okay, what I have done here is I've defined my rejection regions as -2 and +2 with reference to this black colored distribution, which is my null hypothesis distribution. Okay, I've defined my rejection regions, this point here and this point here. If my observed t-score falls on this side of the x-axis, I reject the null, and if it falls on this side of the x-axis, I reject the null. Okay, so these black colored regions are my rejection regions, and these regions will have a total probability of 5%. Take that on trust now. I will explain this in class. But these rejection regions have probability of 5%. So what this means is the null hypothesis is actually true. This is what the null hypothesis distribution represents, right? And the probability of my landing in this region or this region, in the black region, in the x-axis that has the black region above it, right? The total probability is 5%. And that 5% is a type 1 error. It's the probability of my rejecting the null hypothesis when it is actually true, right? I just said that this represents the null hypothesis distribution. So my probability of landing here and here is 5%. So that is the probability of incorrectly rejecting the null. That's my type 1 error. So now I want you to imagine that the true mu is not 0 as hypothesized, but 2. Okay, so this is now a t-distribution that is centered around 2. Now, if this is the true mu, and I mean the true mu is 2 and it's not 0, and I do my null hypothesis significance test assuming that this is the true distribution, this black distribution, then the probability that I will land in the non-rejection region, that means the probability that I will land between +2 and -2, given that the true distribution is centered around 2, that probability is the area under the curve that represents the true distribution. So this probability here is my type 2 error, right? Because this is, if I land within this region, my decision will be fail to reject. Okay, if I land within this region, my decision will be to fail to reject, and the probability of that happening under this true distribution, which is centered around 2, is the area under the curve here, right? So this is the probability of my failing to reject when the null is actually false. That means the null is not equal to 0, the mu is not equal to 0, mu is equal to 2, right? That's why this distribution is centered around 2. So that's why I end up in this with this probability here. This probability is type 2 error here. The probability of my failing to reject the null under repeated sampling when the null is actually false with a particular value for mu. In this case, 2. Okay. So you can see that this number is going to be quite large. It's about 0.5, or it's actually exactly 0.5 in this example, and therefore power is also going to be 0.5. All right. Okay, so these are very important concepts: the concept of type 1 error and the concept of type 2 error and power. Our goal when we do an experiment will be to hold type 1 error at some low value like 0.05 and to keep power as high as possible. So at least 90%, let's say. Okay, I'm just making that number up. In psychology journals, 80% is considered acceptable. Okay, fine. So I want high power and I want to keep type 1 error low. If I have high power, I have low type 2 error, right? Okay. All right, so we have this basic concept of type 1 and type 2 error now clear. And the last concept I want to cover in this video is type M and type S error. So this is a concept that was popularized by Andrew Gelman, who's a famous Bayesian statistician. He wrote a paper in 2014, Gelman and Carlin, in which they spelled out this story of type M and type S error. So the basic idea is the following. Suppose that your true effect size is some number d. Okay. Given this true effect size, we can compute the two kinds of error rates. Just like we have type 1 and type 2 error, these are error rates, we can compute type S and type M error. Type S error is the probability that the sign of your effect under repeated sampling is going to be incorrect given that the result is statistically significant. And type M error, I will spell this out a bit more. I know this is going pretty fast, but I just want to introduce these ideas to you in a video so that they don't strike you as completely new when we come to the class, right? And the type M error is the expectation. Let me state that more informally. Type M error, M stands for magnitude, and what this says is that this is the amount by which you will overestimate your true effect. Okay, so if you have a low power study, what will happen is that when you get a significant effect, the sample mean of your significant result in that low power study will be a huge overestimate. Okay, so if you take the ratio of the true mu to a ratio of your estimated sample mean to the true mu, you will find that number to be 7 or 12 or something big like that. So you will hugely overestimate the true mu when you have a low power experiment. That's called type M error. Okay, so I will now give you a graphical intuition for both type S and type M error. Okay, so that's this figure here. What you're seeing here is a situation where, can I move this? Yeah. What you're seeing here is a situation where we have a true effect size of 15. I'm using the units milliseconds because I do reading studies, and that's the usual unit I have. So this is my true effect size. The standard deviation of the population that I'm sampling from, the population of reading time scores, is 100. My sample size is 20, and I can use some statistical, formulas or functions in R to compute power, and power in this case is about 10%. Okay, that means I have, remember what power is, right? Where is it? Power is this quantity. It's the probability of my correctly rejecting the null when the null is actually false with a particular value, right? So my power is very low in this situation. Power is 10%. I have a 10% chance of detecting the effect if I do a significance test. That means I have a 90% chance of making a type 2 error, of failing to reject the null. That is a very bad situation to be in. But what you will find, and I will show you in the course, of course, that there are many experiments that have such a low power. Okay, and what happens is that if you repeatedly run such an experiment that has low power, what you will find is that in most of the cases, these are the triangles that you're seeing here. The black triangles that you're seeing are the majority of the cases. In the majority of the cases, you will get a non-significant result. That means you will fail to reject the null. Your observed t-score will be, your absolute value of the observed t-score will be less than 2. Okay. But if you repeatedly run this experiment with this low power, there will be a few cases, and these are the circles here, 1, 2, 3, 4, 5, 6 cases out of 50, right, will give you a result such that the observed t is large enough such that you can reject the null hypothesis. What you're seeing in this figure is that true mu, that's 15. This is this horizontal line here, okay? Notice the interesting thing, which is that under repeated sampling, most of your results are going to be null results. Why? Because your type 2 error is 90%. But whenever you do get an effect where you can reject a null, that's this case, this one, this one, this one, and this one, the estimates will be gross overestimates. So look how far away the estimate is. This is 50, the true value is 15. This is about 25, the true value is 15. So you're getting overestimates of the true mu, even though you're taking the sample mean. And these are cases where you reject the null. Okay, so this is an example of type M error here, right? You're overestimating the sample mean when you get a result such that you reject the null. But the other interesting case is that in one case here you rejected the null, but the sign of the effect, not only are you misestimating the true mu, but the sign of the effect is wrong too. Okay, so this has an interesting practical implication, right? So you will often see studies in journals where one day they will say coffee is bad for you, it's going to kill you. Few years later you see another experiment which says coffee is good for you, it's going to help you. Same thing with chocolate, sometimes it kills you, sometimes it helps you. It's the fluctuation of the sign of the effect under low power studies, noisy studies that are being done. Okay, so that's called type S error. The sign is changing and giving you incorrect signs, right? So type M and type S error are two important concepts that we need to keep in mind when thinking about underpowered studies. Okay, and many studies in cognitive psychology in the field that I roughly work in. I'm not a psychologist, but the kind of work that I do is of interest to cognitive psychologists. So I'm very close to that field. So a lot of the work that I do in my field, or a lot of the work that I review or read about, has very low power. So the picture that I'm showing you right now is reflecting the majority of the work that one gets to see in top journals. Okay, in my field, that is, right? Okay, so now so this is the depressing scenario where every time you reject the null hypothesis, you're getting a nonsensical estimate of the mean. By nonsensical I mean an overestimate or the wrong sign altogether. Okay, so that is an insane situation to be in. So the ideal situation is when you're running a high power study. So let's consider a situation where we increase the sample size from 20 to 350, and now we have power 80. So under repeated sampling, so that's what I'm seeing here, this x-axis is representing repeated samples. What happens now is that we get very few situations where we fail to reject the null. So this type 2 error is going to be very low, and the majority of the cases will be such that we will reject the null. Okay, and look at this example. In all the cases, my sample mean is very close to the true mean. Okay, so it's only when, so my type M error is low and my type S error is low. Okay, in fact my type S error is 0 right now. Okay, so the null hypothesis significance testing framework only makes sense if your statistical power is high. This is the only situation where this whole procedure will give you sensible answers. If your power is low, then you're basically in la-la land, right? Because there's only two possible outcomes. One outcome is that you fail to reject the null. So these are the black triangles. You've got no information from this experiment. You wasted your money and your time. The other possibility is that you succeed in rejecting the null, but you shouldn't celebrate, because your success in rejecting the null has led to a misestimation of the true mu, and you might even have the wrong sign. So basically you're barking up the wrong tree, even if you got a significant result, right? So these are type 1, type 2 error, type M, type S error are very important to understand the key point that null hypothesis significance testing makes a lot of sense and can be used in situations where statistical power is high. In other situations, all bets are off. Okay, so that's the background I want to assume when I start my lecture on Monday.